Hi everyone, so this week we're going to wrap up our acid and bases unit and we're going to get started on our liquids and solutions unit. So this first video, you're going to watch a video this week and then I'll have one or two videos for you next week to wrap this unit up. So this first video is going to talk about molarity and concentration. So this is a really relatable topic after we are completing our acids and bases unit. This directly relates to that. So as I've talked about before, when we used hydrochloric acid, so you know from acids and bases now that hydrochloric acid is a strong acid. However, then off of that being a strong acid, the different concentrations of it can make it more or less dangerous when we're using it. We've used 1 molar hydrochloric acid, we've used 0.1 molar hydrochloric acid, and then we've also used 6 molar hydrochloric acid in the lab. So as our molar, meaning molarity, as those molarities increase, our concentration of the acid or given solution increases, which then the danger typically increases as well. So we're going to learn about how to calculate these molarities, which then corresponds to the concentration of our given solution. So concentrations of solutions. So when we're talking about solutions, we're referencing to homogeneous mixtures, and their compositions can vary. Not all homogeneous mixtures have the same exact composition, even when we're talking about the same type of solution, for example, our hydrochloric acid. So we can use these terms dilute and concentrated, however, those are very relative, and for the purposes of scientists, that's not precise enough. It doesn't tell us exactly how much solute we're using in our solution. So we need to know the amount of solute we're using, and this is where we're going to use these types of calculations I'm going to talk about, because this can really tell us how something's going to react and how dangerous it may be. Some of the demonstrations I've done for you in class, I may have started off, especially for you guys, period 1, when you're my guinea pigs, I may have started off a demonstration using a lower concentrated solution, and then may have had to run back to our the storage cabinet and gotten a more concentrated solution so that the reaction worked a little bit faster or more vigorously. So that's where this concentration really comes into play, is all of our reactions that we do. If you notice, every single bottle that we've used in our lab so far have had some concentration on the bottle's label, and now we're going to learn what those labels and those concentrations actually mean. So molarity is our first calculation that we're going to learn how to do. So molarity is represented with a big M, a capital letter M, and it's the number of moles of solute in a given volume of solution. Typically, when we say molar, we're talking about the solute in 1 liter of solution. Obviously, we're not always going to have 1 liter of solution, but when you represent molarity with that capital letter M, we assume 1 liter of solution. And just to remind you, a solute, so that moles of the solute we're using, is what is being dissolved into our solution, just to keep in mind. So that's your formula, and that is also on the back of your reference table on table T. So for example, if we're given moles in liters, so what is the molarity of a solution that contains 0.09 moles of sodium chloride in 0.8 liters of solution? All we need to do is divide the two. So we put our moles of solute on top, our liters of solution, and we get approximately 0.11 capital letter M, meaning molar, sodium chloride. So our solution, if I were to label this on a bottle, to use in the lab would be 0.11 molar sodium chloride. So it's a fairly easy calculation to do. You just need to recognize what is the solute and what is the overall solution, and that's typically an easy thing to find because one's going to be given in moles and one is going to be given in liters. Another scenario we can have is if we're given grams and then also liters, so not moles of solute. This is something we did in stoichiometry, so it shouldn't be too hard for us to figure out. But our first step, instead of going straight to our molarity concentration, our first step is going to be to calculate the gram formula mass of our solute. So if we have the problem, what is the molarity of a solution containing 82 grams of calcium nitrate in 2 liters of solution, we cannot go directly to our molarity formula because we do not have moles of calcium nitrate. So to get to moles of calcium nitrate, we first need to calculate how much 1 mole of calcium nitrate weighs using our periodic table. So I find the mass of 1 calcium, 2 nitrogens, and 6 oxygens, and that would give me a mass of 164. Then I'm going to convert grams to moles. So if I know I'm starting with 82 grams of calcium nitrate and 1 mole of calcium nitrate weighs 164 grams, I can figure out that I have 0.5 moles of this calcium nitrate now. Now is where I can go into my molarity formula and I can put my 0.5 moles over my 2 liters and figure out that this the concentration of this calcium nitrate solution would be 0.250 molar. So again, not a typically hard calculation to make. It really just helps us to determine how concentrated or diluted our solution is. The next type of calculation we can have is percent by mass. This is very similar to the calculation we made when we did stoichiometry with percent composition. It's just the mass of the solute over the mass of solution. They pretty much are the same terms, percent by mass, percent composition, same thing. So you can use that percent composition formula that is on the back of your reference table in table T. So let's look at an example. Percent by mass, so if we want to find what is the percent by mass of sodium hydroxide if 2.50 grams of sodium hydroxide are added to 50 grams of water. So we know we have 2.50 grams of sodium hydroxide, and that's what we want to find the percent by mass of. So that's going to go on top. That is the mass of our solute. And then we have to find the mass of our solution, so the total mass, the mass of our whole. The mass of our part is that sodium hydroxide. The mass of our whole, we need to find the total mass. So in order to do that, we need to add together the 2.5 grams of sodium hydroxide with the 50 grams of water. And then when we do that, we multiply by 100 to get a percent, we get that the mass of sodium hydroxide is 4.76% of our solution that we have. So this, as I noted, is typically how ingredients are labeled on an ingredients label for food. It tells us the percent of, whatever ingredient they're listing of the total food item that you have. So this is a really helpful calculation to be able to make. The next type is percent by volume, very similar to percent by mass, just instead of using grams, now we're using some type of volume, whether it be milliliters or liters, or even cubic centimeters. So for an example, what is the percent by volume of alcohol in 50 milliliters of, if 50 milliliters of ethanol is diluted with water to form a total of 300 milliliters. So here we want to look for the percent by volume of ethanol. So that's going to be 50 milliliters, that's what we're starting with. In this case, we do not need to add the 300 and the 50 because it says to form a total of 300 milliliters. So we already have our total. If it did not say that and it said, for instance, is diluted with 250 milliliters of water, we would need to add the two together to get our overall 300 milliliters. We put the two over each other and we get that ethanol makes up 16.7% of this solution. So you need to pay attention. The only tricky part about these types of calculations that you may find is the wording. You need to just pay attention to whether it's giving you that total volume or total mass of the solution, or if you need to find it, okay? The last one is parts per million. So this is, again, similar to percent composition. However, this is for smaller, when we're working with smaller masses in a bigger total. So for instance, in a swimming pool, there's actually only about 2 grams of chlorine for every 1 million grams of swimming pool water to make a swimming pool sanitary. So if we were to put this into percent composition or percent mass, it would be a very small, very not useful number to us. So that's where this that's where this parts per million calculation comes into play when we're working with these really, really small amounts of solute in a very large amount of solvent. So we use this equation, which is also on your table T on the back of your reference table. Parts per million is the mass of the solute we have divided by the mass of the solution. And now instead of times 100 like we were doing for percent composition and percent mass and even percent volume, we're actually going to multiply this by 1,000,000 to get that unit of parts per million, or ppm. So for example, approximately 0.0043 grams of oxygen can be dissolved in 100 milliliters of water at 20 degrees Celsius. Express this in terms of parts per million. So we can change 100 milliliters of water to 100 grams of water because of its density, and we know that the mass of our solute is that 0.0043, and then we need to find that total mass of solution. So we need to add together our 100 milliliters or 100 grams of water to our 0.0043 grams of oxygen. So that's where we get this number, and then we're going to multiply by 1,000,000, and that's where you're going to end up with that there's 43 parts per million of oxygen in this given solution. So those are the types of calculations we can have in reference to the concentration or molarity of a solution. I will be having you guys make 3 types of solutions with different concentrations and putting up a video on Flipgrid, but I'm going to, I'll be posting the rubric to that on Classroom, as well as an example for you to reference to on Flipgrid. But this is kind of the content of this week that we are going to cover, and then next week we're actually going to cover what a solute and solvent means, and whether things actually dissolve into something or not. For the purpose of this week, we're going to assume everything is mixing together in a nice homogeneous solution. Next week we'll look at where and when that actually happens.